I hope you had a nice break. We didn't actually give you a homework at the beginning of the break, so. So we're going to continue with sequence-to-sequence models. Specifically now, for the current homework, you're all working with CTC models. You're going to be doing a speech recognition task, right? What we saw about these models earlier was that these are a specific these relate to a specific kind of problem where recurrent networks are required, where you have some sequence x1 through xn going in and a different sequence y1 through yn coming out. So speech recognition, speech goes in, a word sequence comes out. In machine translation, a word sequence goes in, a word sequence comes out. What is characteristic of these models is that these problems is that the number of symbols that goes in may not be the same as the number of symbols that comes out. And we saw there were two different variants of this basic problem. The first, of course, was the order synchronous variety, like speech recognition, where something goes in, something else comes out, but the order in which the symbols come out has a correspondence, exact correspondence with the order in which the input goes in. Then there was the other type of model, which was what you might encounter if you were performing machine translation, for instance. So I ate an apple goes in, ich habe einen Apfel gegessen comes out. The order of the output has no direct relation to the order of the input. So here, for example, 8 is the second word. In the output, the 8 is the very last word. Then apple here is the last word, and the output, apple is the second to last word. And in fact, there may be multiple outputs, multiple symbols in the output that relate to a particular symbol in the input, and vice versa. So there's no correspondence. Now, in the last class, in the last couple of lectures, we looked at the order aligned case where you have some input and you have an output, and although the output is not time aligned with the input, the output is order aligned. So what this means is that as you go through the input, you can assign outputs to specific instance of the input. By instant, I'm speaking of the index, and I'm calling the x labeled time, although there, strictly speaking, there doesn't need to be a notion of time, just a notion of a sequence. So speech recognition, for example, you would have some bunch of speech come in, and then the corresponding label for the corresponding phoneme come out. Then some more speech comes in, the label for the next phoneme comes out, and so on. Today, we are looking at the other kind of problem, where the input and the output don't have that kind of order correspondence. So I ate an apple, ich habe einen Apfel gegessen, a sequence went in, a sequence went out, but there is no notion of synchrony between the output and the input. So here, for example, if you will look at what happens here, I becomes ich, ate becomes habe gegessen. So this word ate actually relates to two symbols in the output, and they are very far apart. The an relates to einen, apple relates to Apfel. So you see how things are getting jumbled, right? Now, how exactly do you deal with this kind of a problem? Using recurrent networks. So we've seen, but before we get into that, let's recap a little bit more. Another problem we looked at was that of predicting text. We're going to look at recapitulating this because some of what we learned over here is going to apply. So here was a simple problem. You're given a series of symbols, characters or words, W1 through Wn, and you had to predict the next symbol, the next character, or the next word. So the model would be something like this. You want to learn a model which can take symbols W0 through, say, W3, and predict that the next symbol is going to be W4. Then it would consider W0 through W4 and predict that the next symbol is W5. So it's going to take considering an entire sequence of inputs and predicting the next output. So this, one of the most popular uses for this kind of model is in language modeling, where you might look at a sequence of characters and predict the next character. So if you saw A, B, R, A, H, A, M, L, I, N, C, O, L, you must be able to predict that most likely the next character is the character N. Or 7 years, you've seen 5 words, most likely the next word is a go. So you would like to make this prediction. The way you would train this model, and this is the kind of problem where this applies clearly, right? Now, the way you would train this model is fairly straightforward. You would present it sequences of inputs. Now, what is the training data? Observe that the training data is a sequence of inputs, sequence of symbols, 4, score, and 7 years ago, blah, right? And the output at each time is going to be the next word. The desired output at each time is going to be the next word. So here, after seeing W0, the desired output is W1. After seeing W0 and W1, the desired output is W2. So the divergence that you're actually going to be minimizing is the divergence between the word sequence and a shifted copy of the word sequence, the same sequence shifted by 1. Now, the way you would do it is, first, you realize that the output of the network is not going to be a unique symbol at any time. We saw this in the last class. What the network actually outputs is going to be a probability distribution. So you might have, for the next one is score, the next word is and. This goes through the net. And what is output over here is a probability distribution over all words, right? You're going to get a probability distribution over the entire vocabulary. And in your ideal world, the probability of, after seeing the word for, in your ideal world, the probability of the word score must be 1, and the probability of everything else must be 0. And so your target output is going to be a bunch of zeros, 0, 0, 0, and then at the word score, you might have some output here, but here you want this to be a 1, and everything else must be a 0. That is the desired target output. And so when you compute the cross entropy or the Kullback-Leibler divergence between the desired output and the actual observed output, that is going to have the form minus summation pi log yi, where pi are these target values, yi is the actual probability assigned to the words by the network. And since only one of these symbols has a value, non-zero value in the target output, you're basically left eventually with just minus log of y target, right? So at each time, what you will have is the negative log probability of the target word at that time. And so the total divergence is going to be the sum over all time of these probabilities. Now, when we were generating language, well, if you had once we had trained this, here's what we do. Here the hidden units would be one or more layers of LSTM units. And all of these would be trained, say, using backpropagation. And subsequently, if you wanted to generate some text, you'd start off by giving it some initial seed text, 4, score, and you'd expect it to derive the entire Gettysburg Address. So you say Fourscore and what happens after it sees the word and? It actually computes a probability distribution over the entire vocabulary at that time. And from this probability distribution, you would select a word. You'd select most likely the most likely word, and then the most probable word. And then having selected the most probable word, you're going to treat that word as if this was the word that you actually saw. And so the next word you would see is Fourscore and whatever, 7. And say you drew the word 7, that 7 is going to go in as the next input, and then you'd get a probability distribution for the word after that. And from that probability distribution, you choose a word, which would be W5 over here, ago, and then that goes in as that is treated as the actual input, the actual word at the next instant. And that is used to generate the next probability distribution from which a word is drawn, and so on. And when would you stop? So here is something that all of you must be familiar with. When we speak of a sentence, how do you know a sentence is ended? Pardon me? When you see a period, but you may not necessarily even see a period, right? The period might be part of something else. It might be part of an acronym. So we will designate it, the notion that the sentence has ended is something that is up to us. So typically what we will do is I'm going to say Fourscore and 7 years ago. And if I should choose that after the word ago I decide my sentence is over, I'm going to put a specific symbol over here, which is end of sentence. This end of sentence is not a word. It's an extra symbol that I insert into the vocabulary that I actually stick at the string of words to indicate the termination of a sentence. Now, very often we will also introduce something like this. We will introduce a beginning of sentence marker. And why on earth would you need a beginning of sentence marker? Because the first word in a sentence has a very distinct characteristic. The word the is very likely to occur in the very first position in the sentence. But then think of any other word. The majority of the words are highly unlikely in the first position in the sentence. So the fact that it's the first word actually matters, right? Which means you need a marker saying the next word is the very first word in the sentence. And so very often we will also have a beginning of sentence marker, which I have written as BOS. There are different ways of indicating it. Now, anyway, so when would I actually stop termination over here? I would stop termination when the sentence has ended. Now, in the case of language, the notion of an end of sentence marker is kind of obscure. But suppose you were generating a program. It would be very clear when the program ended. You would open a parenthesis at the very beginning of the program, and then when you're done, if you are generating a C program, the moment you close the parenthesis, you're over, right? So you can continue generation until you see the closed curly brace, at which point you stop. So there's, in many cases, in non-linguistic scenarios, you actually have a very clear indicator of when the termination, the generation must terminate. Anyway, I'm going to assume that we have this special symbol EOS, which indicates the termination of a sentence or the termination of the sequence. This could be a virtual EOS, like in the case of text, or the closed curly brace when you're trying to say generate a computer program, right? Now let's return to a problem. The problem here is I get something of this kind. I ate an apple, and a different sequence comes out. This is very similar to producing text, but there's a difference. Here, first, the output is in a different language, and when the output is in a different language, can you actually know what the sentence must be halfway through the sentence? Can you begin conversion? The fact that the thing is not in proper order means that you have to see the entire input before you actually begin making your conversion. So the situation you have is something of this kind. This model we have seen before. you don't actually begin producing the output until the entire input has been processed. So the simplified scenario over here is you're going to see a sequence of inputs. When the entire sequence of inputs has been observed, then at the final instant, so if you are doing translation of language, this is going to be an end of sentence marker. At this point, once you observe the EOS marker, you begin producing the output only subsequent to that. Now, more realistically, this is not really the model that we're going to be using. We're going to be using a variant of it, and the variant that we will have is of this kind. So this figure here is exactly the same as this model with one extra modification, and the extra modification is this dotted line that's coming back from the top to the bottom. Now, we've seen outputs being fed back to the inputs in recurrent networks earlier. Which were those? Remember? Anybody? No, this was they were the Knox networks earlier, right? So we're going to use a structure somewhat similar to the Knox networks. What will happen here is once this block has finished processing the input, this input is now going to be fed to a second component of the network, which is going to operate on this guy and do the same job that we have here, except at each time something that's drawn from here gets fed back into this into the hidden layers at the next instant. So this clearly has two components. The first one is, so this is what I will call a simple translation model. So it has two components. The first is this one, which takes in the input sequence. So the input sequence feeds into this recurrence structure, and the input sequence is terminated by an explicit EOS symbol, which you would actually insert the EOS symbol once you're done. So 7 years ago, and you're going to stick in the EOS symbol to indicate the sentence is terminated. Now, this you would do for language if you're generating, if you're trying to write a program which read in a C program and produced Java or Python, which you could do using the same architecture, then in that case the closure of the curly brace is going to be your cue that things have ended, right? So once this is done, this portion of the network is going to process the input until it has processed. Yes?
Is there any stochasticity from blue block to yellow block? Because blue block is the only input to yellow block, so blue block is sufficient for generating yellow block. So isn't the hidden there is sufficient to take back to itself instead of output is needed?
Let's watch. Okay. So here I'm going to take an input sequence, and once the end of sentence marker is processed, at that point my hidden units have some representation shown by this red block over here that captures all the information about the sentence that has been fed in. And subsequently, this second recurrent network is going to take this guy and, to answer Swapnil's question, some extra inputs and produce outputs. And this will generate output sequences, an output word sequence. And when will it stop generating the output word sequence? The moment it encounters the end of sequence marker. So here's how you would actually expect it to operate. You produce some word sequence, you process some word sequence, and when the final word in the sequence has been processed, you're going to use that feed that to the output layer of the network, which will produce the first word. And then both the hidden and the output, both the hidden values and the output are fed back into the hidden layer of at the next instant, which is going to produce the next output. And this process continues until the end of sentence marker is generated. I still haven't answered your question, but I'll get to it. So in all of my figures, I'm going to assume that there's just one hidden layer. But this little blue box or the little green box that I've shown is a magic box which can have any complicated machinery inside. We aren't really particularly concerned about the complexity of the machinery. So it could, for example, be something like with 2 layers, could be anything else. Just for simplicity of illustration, I'm going to assume that there's only one layer. Okay. Now this entire machine can be partitioned into 2 blocks. The first block processes the input and learns a hidden representation. The second block consumes this hidden representation and generates an output. So I'm going to call this first block an encoder. The second block I will call a decoder. So an encoder encodes the input. The decoder decodes the encoded input. And so you're going to be encoding English and decoding it into French, or encoding Spanish and decoding it into Latin, or whatever else you might want to do, encoding C and decoding it into Python. Now let's get into the details. I'm speaking of words over here. How exactly do I represent the words? I'm going to be representing words as one-hot vectors. But then, as we saw in the last class or 2 classes ago, I'm not really going to be feeding one-hot vectors into the network. What we will do is to zap the one-hot vector down using some kind of a projection into a lower dimensional vector, because as we saw, one-hot vectors are very wasteful in their usage of the space. And so if you project it down, you're going to get a more dense usage of the space, and hopefully also do a better job of capturing relationships between words. And those are what we will call embeddings. And it's these embeddings that are going to be passed into the network for processing. And now the one-hot representation of the input is very different from the one-hot representation of the output. Why so? Think of the problem of translating English to French. The vocabulary for English is very different from the vocabulary for French. So I might have, for example, just 10,000 words in English, but if I want to translate it to French, maybe I need 15,000 words. In order to translate 100,000 word in vocabulary in English into Russian, the output would have to be 400,000 words. So the dimensionality of the one-hot vector in the 2 cases is going to be very different, which also means that this matrix, which projects the one-hot vector down into a lower dimensional representation, is going to be different for the input and the output. So here, although I'm just writing words, the implicit assumption is that these things are being represented one-hot and being projected down using some projection into an embedding space. And so also the outputs are being represented one-hot and being projected down into some embedding through an embedding matrix. Now, I'm not going to show these P's in subsequent slides. They are implicit. They are always there. Just remember that anytime you see the slide. Okay? And now to get to your question, where does the stochasticity come in? Why do I need to feed things back? So at each time, what does the network actually produce? The network is not going to produce just pop out the word ish. It's actually going to produce a probability distribution over all words in German in this case. And so if it produces a probability distribution over all words in German, what it is producing is, at the first time instant, it's going to be producing the probability of, German word given the sequence of English words. You fed the entire sequence of English words, it's producing a probability distribution over the German words, right? Or let me put it now. Yeah. So how do you generate a word then? The word must be drawn from this probability distribution. And one thing you could do is to simply pull out the most likely word, right? And whichever word had the highest probability, you could just pick it up. So what you would get over here is this is going to be this is your vocabulary in German, and you would have a probability distribution over the vocabulary. You're going to have to choose one word from it. And maybe you say, okay, this guy has the highest probability, so I'm going to choose this word. Right? Now, you choose the word, and that word is going to be fed back into the net at the next instant. So the stochasticity comes from the fact that you're choosing something from the distribution. And now, and as a result, at the next instant, you're going to have some other probability distribution. And this is the probability. What is the probability distribution now? It's no longer this guy, because at this point, there's some extra information. So at the next instant, the probability distribution is actually going to be P of Wg given We1 through n, followed by Wg1, because the first German word has already been produced, and that is, you're assuming that that is a given for the next instant, right? So at the next instant, you're producing a conditional probability distribution conditioned on the entire input and the first word that was selected. And then from this distribution, you're going to choose a word. And that goes in to the next instant, and now you would produce another probability distribution. And in this probability distribution, now what you're actually going to be producing is not this, but right? You get that. So, and you would continue this process until eventually you chose the end of sentence marker. Now observe that EOS is part of the vocabulary for English. It's also been included as part of the vocabulary for German, because you need to know when to terminate. In the absence of information about when to terminate, you're going to keep producing stuff forever. And you will almost, you will certainly produce rubbish if you do that, right? Now, how do you actually choose the word? Yes?
How well does the network model the whole probability distribution of the vocabulary? Because there's almost like 500,000 words to choose from.
For English, it's 100,000, but German, yeah.
Isn't that become difficult to choose over such a big distribution?
Strangely enough, it actually does an amazing job. So so long as the network has a sufficiently large number of parameters, it's really good at learning these distributions, which is why you get you get amazing results with Google Translate, don't you? So it's network actually learning this distribution. Now, when I choose a particular sequence of words, right, what exactly am I choosing? So let's say I chose the words O1 through OL. Then in the process, I have chosen the sequence of probabilities. The corresponding probabilities are going to be, if Y represents the output of the network at each time, it's going to be Y1 O1 times Y1 should be Y2 or Y1. There's some bug over here. I'll fix this. But basically, at each time, it's going to be Y1 O1 times Y2 O2 times Y3 O3 times Y4 O4, right? So you're going to be picking the probability of Abwehr-ish over here, the probability of Habe over here, probability of upfill over here. That sequence of probabilities gives you the probability of the output that was chosen. And what you're really computing is when I multiply all of these probabilities, what you're really computing is, because at each time you're getting a conditional probability, right? So the product of these probabilities is simply going to give you the product or the probability of the output sequence given the input sequence. Very simply, because at each time at the first time it's going to be the WG given the English. Second time it's going to be WG given the English times the first word. If you multiply these things out, simple Bayes rule, you're going to get the probability of the output word sequence or the output symbol sequence given the input symbol sequence. So our objective is this. Here is an English symbol sequence. What is the most likely sequence of words in German. We want to pick the most a posteriori most likely sequence of words in German given the English sequence of English words. And if I simply choose the most likely word at each time, that's not going to do the job. Why is that? So if I just pick the most likely symbol at each time, that may cause the distribution to be confused at the next time or somewhere downstream, and choosing a different, less likely word early could cause the distribution at the next time to be more peaky, resulting in a more likely, overall more likely output. So to give you an idea, say let's consider this hypothetical problem. I've switched the problem context. Let's say you're performing speech recognition, right? So the very first word you output was the word he. So the input was speech. You're using the same model. The input was speech. Now the output is a sequence of words. So the very first word was he. And then at the next time instant, you found, the next output, you found that the most likely word was the word nose. Now, he knows, with the word he knows, with the nose representing the feature on your face, that's not a very likely pair of words. So given this pair of words as the input, when the network is asked to produce a probability distribution over words at the third instant, considering that this is something you can't really make sense of, you can't really be sure what the next word is going to be. So the probability distribution is likely to be uniform or close to uniform over all the words because it's very confused. On the other hand, at the second time instant, maybe this word nose with a K has a lower probability than the word nose representing the object on your face. But if you chose nose over here, then at the next instant you might get a probability distribution of this kind, where he knows something. The probability for the word something is going to peak, given as opposed to other words, right? And now, if I chose the most likely one over here, say, the total probability of this word sequence is going to be higher than the total probability of this word sequence, although nose was more probable than knows, simply because the influence at the next instant caused the probabilities of the next instant to be to skew in a very bad way in the first case. And so making a bad choice, even though it was locally more likely at the second instant, can kill the overall probability. Now, the problem is, when you're going left to right, there's no way for you're outputting the first word, and then you're outputting the second word. Now, in the big picture, when you're outputting the second word, there's no way for you to know the influence of the specific word that you chose on the probability distribution at the next instant. So when you're over here, you don't know that although the word knows is more likely, choosing it is going to result in a bad probability distribution at time 3. So, and in fact, the influence may not be immediate. Choosing the word nose over here might cause the probability distribution to get flattened 5 words down. So the consequence is not even immediate. So the choice of a wrong word early can actually cumulatively lead to a poorer overall score over time. And in fact, this goes back, right? Even the very first word, how did I choose the word he? If I had chosen the word thee, and let's say thee was slightly less likely than he, then if the first word was thee, then the word nose at the second word becomes much more structured. The nose will give you a much better probability for the third word than he knows or could, right? So the point is that the influence of making choosing a word at any point, committing to a word at any point, is actually not going to be felt for a very long, can often not be felt until very late into the output. And if you want to pick the overall most likely word sequence, you don't want to commit. If you don't want to commit, how do you actually deal with the problem? Here's what you can do. At the very first time instant, you just clone your output network. You clone the output network as many times as there are words in your vocabulary. And so you're going to have one copy of the net for each of these. You obviously do know the probability assigned to each of these words because these were all drawn from the output over here, right? And then for the next word, you're going to have a probability distribution over here. You clone the network k times again. And then you clone it k times again. You just generate the entire tree. And now, having generated the entire tree, you can keep going forward until one of them produces an end of sequence symbol. And you can trace your way back and see what was the overall probability of that sequence, or are there other sequences which are more probable, and you can keep continuing the process. Now, what is the problem with doing something of this kind? It blows up very quickly. If I have a vocabulary of 100,000 words, the first time around I'm making 100,000 copies. Okay, not so bad. The next time I'm making 100 million copies. This is bad, but maybe you can still manage it. But the very third word into your vocabulary, you're speaking of a trillion copies, right? So things blow up really quickly. This is not going to work. If you have a vocabulary of V words, over T symbols, you're going to fork out into V raised to T branches. So how do you deal with it? We prune. We encountered this term beam search earlier. They're going to say this is basically what you'll be doing even over here. So at this time, I have made k forks, but then each of those k forks has I have made V forks, right, where V is the size of the vocabulary, but each of those guys has a probability. So the word the was assigned a probability at this time. The word we was also assigned a probability at this time. So each of these words has a probability assigned to it. I don't just expand all of them. I'm going to expand only the k most likely words. And so now I'm going to get k copies of the network over here. Didn't really help me. The next so maybe I have k equals 2. I'm going to kill everything else. These two guys are retained. But it doesn't really help me because those two at the next instant are going to give me 2 times V branches. But guess what? I can repeat the same process. Of these 2 times V branches, I just retain the k most likely. And when I speak of the k most likely, the probability of every single one over here is going to be the product of these probabilities, right? The probability of the first word and the probability of the second word. The probability of the first in each case. So there's going to be he, I, he knows, he whatever, the I, the knows. So you're multiplying the probabilities of the first 2 words. And over that pair, you would choose the top k, and you'd retain only the top k and prune the rest. And then those k are going to be expanded again. And then again, those k, now you're going to have a probability of the total probability of any particular symbol, any particular branch is the product of 3 probabilities over here. You're going to choose the top k amongst those and retain only those and keep going forward. At each time, the probability of any particular branch over here is going to be the product of the probabilities from here all the way until to the end of the branch. And you can keep continuing this. You can keep going forward, retaining only k of these symbols at any time. And when do you terminate, right? I can keep going until one of them hits an end of sentence symbol. Now, is this the right time to say, okay, I'm done? This is the output? Not necessarily. Why? Because it might turn out that this sequence of probabilities is actually lower than this sequence of probabilities. So this guy can no longer continue. He's terminated. He's stopped, right? So now this one would continue, and the top k is going to be emanating entirely from here, and they would continue to be extended till one of them produces an end of sentence symbol, and you go on. And eventually you're going to get one sequence where you find that the probability of the sequence is higher than any terminated sequence earlier, and also higher than any subsequent terminated sequence. And that is going to be your best guess for the output. But this also gives you a natural mechanism for saying, what is my second best guess? what is my third best case? I can keep continuing this, extending this till till I get many end of sentence markers, and each of them is going to give me a different guess. So I can actually produce my top however many number of guesses, right? So we see how we can actually, given such a model, we see how we can produce an output, how we can translate one sequence to another. But how do you learn it? So here's the problem. The training data is going to be something of this kind: I ate an apple, end of sentence. And the output, desired output, is ich habe einen Apfel gegessen, end of sentence. So this is what you really have. In the ideal case, if the network were functioning perfectly, then after having seen I ate an apple, it would produce the word ich exactly. And then if you fed it ich, it would produce exactly the word habe, right? So the actual input that the network gets is not merely this guy, as you can see, interestingly enough. The actual input is going to be a concatenation of the input and the target output. And the target output and the target output that you actually use to compute your divergence is going to be the target output itself. So observe that this guy is simply this one shifted one left. And in the training the network, what you're actually feeding to the network is first the English and then the German. So it's a concatenation of the input and the target output. So during the forward pass, you would actually give it the X, the English here, and it's going to produce outputs, but then you would give it the actual German out here, and it's going to produce a probability distribution. The target outputs are the German sentences. You can compute a divergence between these two, and standard backpropagation you could, yes.
Are we making sure that it starts producing the output only after EOS, or are we just considering the outputs that is produced after EOS?
So these two portions again, observe that the network is, I have to go back quite a bit, unfortunately. The network has two distinct components. I use too much animation for these things to be convenient, but yeah. The network has two distinct components, right? This component doesn't begin to activate until this guy is done. So the structure naturally ensures this. Only after the EOS has been processed are you going to pass this and begin producing things from the next network, right? Where were we? Out here in training somewhere, right? Okay. Now observe that something interesting is happening over here. We need not have actually given the actual input out here. This, whatever mechanism you choose for drawing values from the output is going to produce some value out here, right? And those could have been fed back. And the entire network could have been optimized to make sure that even the drawing process is appropriately done. Unfortunately, this actually ends up being way too complicated. So this is a teacher forcing. You're actually telling the system what the output must have been, even in the input portion of the network. Now, in practice, if you're using stochastic gradient descent, you're not actually going to be using this entire sequence. More often, what is done is that you randomly sample one or more words from the output and only pass the gradients, the derivatives for the gradients back from those randomly chosen words. So within each iteration, for each input, you're going to select one training instance, which is an input-output pair, a sentences, input sentence and an output sentence. Do the forward pass, produce a sequence of outputs, then randomly select maybe a single output over here, just randomly. Use just that one derivative and pass it backward to learn both the parameters of the decoder, which are out here, and the parameters of the encoder. So the overall training is going to be something like this. Given several training instances, during the forward pass, you compute the output of the network. Observe that both the x value and the d value are used in computing the output. During the backward pass, you compute the divergence between the desired target output and the actual output and propagate derivatives backwards for updates. There are some standard tricks that people have used. Now, the concept is very nice and clean, but there's the concept, and then there are the tricks of the trade. So various tricks have been proposed in the literature. One common trick that was proposed early was to feed the input in reverse order. So you start with the end of sentence symbol and go backwards to the first word. And sure, it turns out that things turn out to actually work out better this way. And that's simply because this I is much closer to the ish. And so if you look at it, you get a much better chance of picking the first word, getting the first word right than the other way. Now, this could also have been processed using a bidirectional network, and the whole thing would still work, right? Now, feeding the input in reverse order happens both during training and during testing. Obviously, whatever you do during training must also be done during testing, right? So here the overall, this modified training is going to be the same as the one before, except that the input would now be fed in reverse order. So where would you use this sort of thing? I've been using machine translation as an example, but in fact there are many different applications. Machine translation, English goes in, German goes out. My name is Tom, mein Name ist Tom. Or speech recognition. A speech recording goes in, a word sequence or a phoneme sequence or a character sequence comes out. Dialogue. The input can be the user's input, and the output can be the system's response. So I have a problem, and the system comes back with, how may I help you? Now, this is not even a translation problem. They're completely unrelated text at the word level, but there's a definite relationship in that one is a response to the other. And so so the same kind of architecture applies even over here. Or converting images to captions. And now, firstly, one of the key aspects of all of this is that you're expecting the encoder to capture the essence of everything that is in the input. So if I gave you a word sequence, I ate an apple, this hidden representation that you learn, that you compute at the end of the input, is all that's being fed to the decoder. So this hidden representation must ideally actually learn to represent the entire input, regardless of the length of the input. And here are some results from Sutskever and co., where they show that this in fact happens. So here, after having trained the system, they actually show a two-dimensional visualization of the hidden representation obtained using, I think, PCA. And look at how things cluster up. John admires Mary. John is in love with Mary. John respects Mary. All of these come close to one another. You flip it and you say Mary admires John. Mary's in love with John. They have the same kind of relationship as this guy, but the two groups are very far apart. Or I was given a card by her in the garden. In the garden, she gave me a card. She gave me a card in the garden. All of these mean more or less the same thing, and they cluster together. She was given a card by me. In the garden, I gave her a card. I gave her a card in the garden. So these things have the opposite meaning, and you see those three things cluster together in a different region of the space. So it appears, at least empirically, that if you cherry pick your examples, which is what I suspect the authors did, you actually get some nice clustering of the representation that you actually get. And here are some examples they gave of the kind of machine translation that they actually obtain. Does anybody know French? We have no way of knowing whether this is good or bad, right? So we're going to go by faith, and I'm going to claim that their model was pretty close to the truth. Now, if you actually look at the outputs, they actually look pretty close, right? At least to my naive, un-French trained eyes. If this had been Spanish or German, I could have told you it was better, that was better or not. Or here's a human-machine conversation. So the machine leads out with what is the error you're running, please, and the human says, I'm seeing an error related to VPN. What is the error message you're getting when connecting to VPN using Network Connect? Now all of this is being produced by this little translation model that we just saw. And as you can see, it's doing a pretty good job of actually holding a fairly reasonable dialogue with this person, at least in this particular example. Or generating image captions. This is a particularly fascinating one. Now this is not really a sequence-to-sequence problem, right? This is a different problem where you're given an image, which is one modality, and the output is a sequence of text, which is an entirely different modality. And it turns out it works just fine over here too. So here, you're going to replace the encoder. Now the problem we had was the architecture we had an encoder and a decoder. So the encoder worked off English and produced a hidden representation. And then the decoder used this hidden representation and generated German in our example. In image captioning, the encoder is going to be replaced by an image classification network or an image processing network of some kind. So here, the initial state is produced by a state-of-the-art convolutional neural network-based image classification system, except that you don't just use the classification output, you could use any of the any intermediate representation from it as well. This is the hidden state that's now fed to the language decoder, which now produces the word sequence. This is basically exactly the same architecture as what we saw before, except that the encoder has been replaced by a CNN. So observe that this looks very much like what we had before, except this portion has changed. So the way they would do it, you have, if you were decoding, you'd be given an image, you process it with the CNN to get an output for the classification layer, or it doesn't really have to be the classification layer, but this was how it was actually originally presented. And now this is used in the standard decoder setup to produce the word sequence. Now in practice, this decoding would use the beam search that we spoke of earlier, right? And how about training? Training is exactly the same. Now the data you'd be given are images and their captions, and so you're going to use the image to obtain a hidden representation. Then you'd give it, and the actual desired captions would be fed in. The output is going to be the caption shifted by one word, and you would compute the cross entropy between the desired caption and the probability distribution output by the network, and use just straight up backpropagation to train everything. The one key difference is that in these models you typically don't update the encoder, because the encoder comes from a different modality, and you can use you can basically depend on transfer learning, learn it on an actual collection of images to learn to extract good representations for images. And so this is what is done. And I think the primary reason for doing this is that you're much more likely to have a very large collection of images and a much smaller collection of images with captions. And so it doesn't make sense to use your captioned images to update something that's been learned on a large collection of images alone, right? Now, how well does that work? Here, at the very beginning of the course, we saw these examples in class. And it's surprisingly good, right? This is a man in black shirt is playing a guitar. So clearly the image classifier, the CNN, has recognized the guitar, it has recognized the man, it has recognized the black shirt, which is why the language generator is able to use all of those concepts and stitch them together into a reasonable sentence, right? Or here, a construction worker in orange safety vest is working on a road. Very true. Two young girls are playing with a Lego toy. Well, I don't know if there's a young girl or not, but the concept is right. Boy is doing a backflip on a wakeboard. I don't know if there's a wakeboard down there, but he's definitely doing a backflip. And it gets things wrong, but it's kind of understandable. So this is a baseball bat, clearly. This is a cat. this is a woman, and it's her teddy bear, right? And there's a horse here, but you can't see it. It's invisible. There's an invisible horse. So it makes actually it's a very intuitive program which can see things that humans can't. But yeah.
I know there's a difference between this model using CNN as encoder, since the output of the CNN is not actually a sequence of words.
It's just a collection. It's a probability distribution over words. So what is happening is that this decoder is actually learning to use the most probable words in the output in the appropriate locations. Yeah. So so the language. So there's no guarantee that the sequence of words that you get is actually going to be meaningful, right? What it's doing is producing a high probability word sequence, which incorporates the high probability concepts from the image. And that simple act seems to produce the right captions. It's pretty impressive that that's all it really does. And here's an example of something very similar where they actually do this for video. You have an input video, several frames. Each of them goes through a CNN. You're going to get a mean pooling pool, which produces a single representation, which goes into this recurrent network for producing a video caption. Now, observe the difference between this architecture and the one that was used earlier, that the hidden representation derived from the video goes into every word. And in fact, you could do this for the images as well, right? Just to make sure that everything gets used just right. Anyway, so moving on. So this framework works. It's actually very simple. It's very convenient. And there's a problem. All of the information about the input sequence is being embedded into this one single vector, which is the hidden node at the end of the input sequence. So basically, we are overloading this one node with a lot of information. Regardless of the length of the input sequence, you're trying to squish all of those into that one node, and that doesn't make a lot of sense. In reality, every one of these hidden representations carries information. And each of these carries a lot of information, local information about the specific word that it saw at that time, and also some global information about everything that happened before it, right? So when you go down this guy, the information about the first word I gets diluted by the time you get to the end, which is why they found it convenient to flip the order beginning to end, if you will remember, right? So now this is not a very nice thing to be happening. Also, flipping the order means that this guy gets something that's occurred immediately in the past, but what about something at the end? Now, if you look at the output and compare it to the input, you observe that different regions, different symbols in the output relate to different symbols in the input. So here, for example, ish relates to I, habe relates to 8, but then gegessen also relates to 8, because habe gegessen is 8. Einen relates to an, Apfel relates to apple. So you see that the exact word in the input that each word in the output relates to best can be anywhere in the input. And if you're waiting to compress, just look at this one guy, that information might have been diluted or even lost. So what we really want is some way to feed inputs the information about every one of the input words when you are producing every one of the output words. So something of this kind potentially, right? That this guy goes into every one of these decoded words. So does this guy, so does this guy, so does this guy. What's the problem with an architecture of this kind? It's untenable. Firstly, you don't know how many words are coming in. So you don't know how many connections are going to come in. It's going to be over-parameterized, and the model is simply not specifiable. And once you say I'm going to, and if you say, instead of looking at the entire input, I'm going to look at just k symbols from the input, you're left with the problem of figuring out which k. And pretty much all of the problems we are speaking of so far sort of just roll over, right? So instead, this is where we come up with the notion of an attention model. It's very intuitive. That attention models are beautiful. And they are almost a logical progression from, so if you looked at what we've done so far, recurrent networks are a logical progression from multi-layer perceptrons. And recurrent translation models are a logical progression from standard recurrent models. And attention models are a logical progression from what we just saw. So we're still going to use the same encoder-decoder framework, but we're going to separate the two. And now, at each time, instead of simply using the final hidden representation, yes?
You said you want to separate the two, so where the parameters shared between encoder and decoder before?
No, never.
They're still different.
They're just still different, right? So what I mean by separate the two is I'm not, instead of simply directly passing things in, I'm going to consider things slightly differently. Okay? Here's what we do. Instead of just looking at this one hidden representation after encoding and passing it to the decoder, I'm going to assume that every one of the hidden states in the decoder is going to look at every one of the hidden states in the encoder, except that each one of these is going to get a weighted combination of the hidden states in the encoder. So if you have a weighted combination of this kind, then you have the possibility that the word apfel over here will somehow be able to focus on apple, that the word gegessen over here will be able to focus on the word ate. But the moment I say that, then what is the natural consequence? That for apfel to be able to focus on apple, it must give most weight to H3. For gegessen to be able to focus on ate, it must give most weight to H1. So the weights that you have end up being dependent on the symbol that you're trying to be producing at this current time. So the weights vary with output time. Now this again breaks down, right? All of the architectures that we considered had a fixed set of weights, and now we are speaking of weights that actually vary with the output, with the current input, right? So how do we actually come up with a set of weights that varies with the output time? Here's how. So again, just to recapitulate, we have all of these weights. The set of weights for each of these guys is going to be different. The input to the hidden decoder layer is going to be a weighted combination of these hidden representations. These weights are obviously scalars because you're computing a weighted combination of these hidden representations. The way we will do it is to make these weights a function of the current state. So what do I mean by that? Let's say I'm trying to produce the word gegessen, right? The state over here is going to say that I've already produced information relating to the word ate or apple, right? Apfel. So knowing that this guy over here has ich habe einen Apfel gives me information that the next word I must be producing has to do with, must relate to something, must have some relation to the act of eating. So the weights that I will use to combine these hidden representations to input to this guy are going to be a function of the hidden state here. Make sense? So the weighted combination of inputs that I get, use some weights. The weights that I will use at time 5 are going to be a function of the state at time 4. So ich habe einen Apfel means the next word has to do something with apples, right? So this state carries information about what is likely, what is plausible at the next instant. So I'm going to be comparing this state to all of these guys to decide which of the ones in the input I must be focusing on at the next instant. Get the intuition? And the way we will do it is we will actually have a weight which is some function. The weight assigned to each of these guys is some function of that hidden representation. So in order to produce the input at time t, the weight that we will compute is going to be a function of the hidden representation and the state at time t minus 1. So gegessen is the W5. So in order to compute the weights at time 5, I'm going to be using the hidden representation at time 4. That has the key, that has the Q, right? And so these weights are going to be some function of hi and st minus 1. Now, it can't just be an arbitrary weight. The problem is if I choose an arbitrary weight, our weights can be any number. And so the weights are any odd number. If I have a collection of real valued weights, then if I just do a weighted combination, there's no bound on the weighted combination of the hidden representation that goes in over here. So I really want the weights to be a distribution, which tells me which of these guys to focus on. So when I computed a weighted combination, it's a convex combination of these hidden representations. So what we will do is to partition it into two problems. First, we compute a raw weight for each of these guys, but then these raw weights are normalized using a softmax such that these raw weights over the entire input sequence of inputs becomes a distribution. And so now you're going to get a probability distribution over the inputs. And when you get a probability distribution over the inputs, that's going to have a high value for some guys and a low value for other guys. And so hopefully, after ich habe einen, if you're going to be using the state S2, the state S2 encodes the fact that in German you've said I have an, which means you're looking for something that relates to that. And amongst all the words that you have in this input sequence, apple is the one that fits best. So apple is the one that's going to get the maximum weight. And then you would use that combination to produce the hidden representation that goes into the next time instant, to produce the next symbol. So what kind of a function could we have that actually compares this hidden representation to this guy? Various functions have been proposed. So the simplest one is to just say I'm going to take the inner product between this S3 and the H. But to take the inner product between the two, those two must have the same dimension. So if the two are different dimensions, then you can connect them up by having a weights vector, a weighting matrix WG in between the two. And now this weighting matrix WG becomes something that must be learned. Or in the very first paper on attention, they actually had a much uglier function, which was this guy, where they concatenated the two, computed a weighted combination, put it through a tan H, and then used an inner product with yet another vector. Now, if you look through the literature when you do homework 4, you will observe that there's some terminology that's used when they compute weights, key value pairs. So the key, they would think, this is what you use to decide what weight to assign to each of these guys. So this guy would be called the key, and these are the values, and so you'd be combining the two to compute these weights. So in the forward pass, so the way the whole thing would work, you pass the input through the encoder to produce hidden representations, and then having done that, observe that the decoder needs an initial state. The initial state is often derived from the final state of the encoder, either directly or by some weighted transformation where the weights must be learned. And then subsequently, using this initial state, you can compute a weighted combination, compute weights for all of the inputs, compute the weighted combination of the lot, and feed that to produce the first word for the decoder. In addition to just this guy, you also need an initial word, which could be something like a start of sentence symbol. And then you produce an output, produce a distribution from which you choose an output. Now using this state, you compute a new set of weights, compute a new hidden representation, which is fed in along with ish to produce the next word, and you continue the process. At each time, at each time you use the state to compute compute weights and a weighted combination of the hidden representations from the encoder, and feed that into the decoder to produce the next output, right? And the whole thing continues till you generate an end of sentence marker. So once again, the idea is to produce the most likely output word sequence, and as we saw earlier, this is exactly the case as the earlier decoder as well. Choosing a word out here means that you're committed. And if you're committed, you may end up with a suboptimal sequence of words. So what you really want to do is, again, the same trick as before, just keep splitting your decoder and pruning to get the most likely sequence of words, right? So what exactly does this attention learn? Turns out that in order to produce each word, you're actually computing a weight over all of these inputs, And it turns out that when you actually plot these guys, you find some very interesting patterns. So this was examples from Bahdanao et al., where they were translating English to French. And what they have done here is, this is the input. So for each word, they plotted the weights over the input as one row in this picture, where the grayscale tells you which one gives you, the black is 0, white is 1, and so the grayscale tells you how much attention was paid to each word. And so the agreement on the European Economic Area was signed in August 1992. The word "the" translates to the word le in French, and you will see that it actually learns to pay the most attention to the. Similarly, agreement becomes accord, and you can see that it pays the most attention to agreement. Here's the most interesting bit. In English, you say European Economic Area, but in French, the order changes. Zone économique européenne, right? And so when you actually look at the attention that's paid, when it's producing the fourth word over here, it automatically learns to pay maximum attention to the word area in English. The fifth word is economic. It automatically learns to pay the most attention to the word economic. The sixth word is European, and it learns to pay the most attention to the appropriate word in English. And in each of these examples, you find exactly the same pattern. It actually learns. The general trend is kind of linear, but locally you find that it learns about these reorderings and learns what to pay attention to. And more translation examples where we have to trust their translation, right? So we've seen how a trained network can be used to compute outputs, but how about training? Same thing. This is exactly the same as before. You would have an encoder, and then you would actually give it the actual outputs to produce probability distributions, and then you can use the target outputs to compute your divergence and backpropagate. Except now there's one key difference. During the backpropagation, you're also going to be updating the parameters of the weighting function g in order to learn what to pay attention to. So there have been various coming to the end of this, there have been various extensions to the model, things like local attention versus global attention, whether you decide you're going to be paying attention to everything or focusing on something really small. Bidirectional processing of the input sequence. Once you separate the encoder and the decoder in the manner we just did, there's no need for the processing of the encoder to be unidirectional. You could look at it both ways and then use those hidden representations in combination, typically by concatenating the two in the decoder. The decoder must be unidirectional, but the encoder can be bidirectional, right? And another thing that is often done is instead of various tricks of the trade, things like teacher forcing, instead of passing the actual input to the output, you occasionally pass something that is sampled from here to learn about the noise that might happen when you're in the process of actual translation, right? When you're in the process of actual translation, you're not actually going to get a perfect input to the decoder. You're going to get something noisy. And in order to be able to deal with that, sometimes you randomly choose some locations where instead of using the actual output, you draw it from the probability distribution and various other tricks. So there are really, really nice results using attention-based approaches. I'll stop the lecture here. I won't go over I have an example or two. I won't go over it. But this is going to be a significant component of both the quiz this week and homework 4. So hopefully you will get to learn a lot more about how attention-based models work over your homeworks. Right? Thank you. Questions? No? Thanks.